Today, welcome to the SPCL Vcast this week, and we're super happy to have Manya Ghobadi here to tell us about the high performance networks or machine learning specialized networks, but that's of course also high performance. And Nikolai is going to introduce her now in detail.
Thank you, Torsten, and again, thank you, Manya. Manya is an associate professor in the Electrical Engineering and Computer Science department at MIT. She received her PhD from the University of Toronto, after which she spent some time at Microsoft Research and Google. She's done lots of work in many areas, focusing on computer networking. She has won a Sloan Fellowship, an NSF Career Award, numerous Best Paper Awards, and so on. And with that, I'll let Manya take it away. Thank you.
Thank you so much, folks. Hi, everybody. Thank you for attending this talk. Let me just start by sharing my screen. Okay, can everybody see this?
Yes.
Perfect. All right, thank you. So what I want to talk about today is next generation networks for machine learning. Let me move the zoom control so I can see. Okay. So let me start by a graph that shows why we should, as networking and systems researchers, start thinking about machine learning as a workload. This graph here is showing the growth of the compute requirements of machine learning models over the years. And so what's fascinating to me is that there's about every 2 years, there's about 100x growth of machine learning models. But then if you compare this with our good old Moore's law that we've enjoyed for the several decades, Moore's law grows only 2x every 2 years. And so the growth is crazy. It's crazier than what I have seen. And so the question is that, what should we do with such a growth? So, I mean, naturally, the way industry would respond to a growth in size is to distribute large DNN models across data centers. But then what seems to be happening these days is that existing data center networks are becoming bottlenecks for large-scale distributed jobs. And I'll show you evidence of this. But then this gets me thinking. The high-level idea that I want to convey throughout this presentation is as follows. What I want to do and I want to show you is to leverage the traffic pattern of machine learning workloads to build something I call ML-centric clusters. Throughout the talk, I'm going to show you traffic pattern, both in terms of time and also in terms of space, like say, think of it as a heat map. And I want to argue that this traffic pattern is special and it's different from the legacy data center workloads that we're all used to optimize. So, okay, building ML-centric clusters seems like a good idea, but it is not that easy. It's challenging because we have to have a deep understanding of ML workloads and their communication collectives. Without that, we can't really build an ML-centric cluster. I'll show you at the very beginning of the talk too that building ML-centric clusters actually requires breaking some orthodoxies in the way that we are thinking about network infrastructures and protocols. And it also requires us to co-optimize the network with the workload. But it's also impactful. I'm going to show you throughout the talk that an ML-centric cluster can run training at up to 3.4 times faster, or we can make the network 3.2 times cheaper. And so this work is in collaboration with Meta and also Google, but Meta in particular is very interested in augmenting their ML game, and they're looking into deploying some of our ideas. So the way I've designed the talk, I have 3 kind of topics that I want to talk about. I've designed the talk in a way that most of the time I want to spend on the first 2 topics, and then I'm going to spend maybe the last 5 minutes talking about a very exciting ongoing work in my group. But first, I want to talk to you folks about congestion control in ML jobs. So just a quick background about what I mean when I'm talking about deep neural networks and training. Basically, the most common approach for training a neural network is called stochastic gradient descent. And the way it works is that imagine there's a model here in the middle, and there are some data here that we want to train this model on. As an SGD iteration involves selecting a random batch of these labeled training data, then computing the error over the model, and then updating the model weight based on this computed gradients. And so training iterations are repeated with a new batch over and over until the model converges to the target accuracy. This is all good. And so what are we doing here? Our goal is to accelerate the training time, to make the training faster, basically, by distributing the data or the model or both of them in a data set. Imagine that the model here, this is a very simple model. Imagine the model is massive, or imagine if the data set is massive. And so distributed training ends up distributing all of this model or the data or both of them across nodes. And what we want to do is to make sure that training is actually accelerated when we are distributing. So, like I said, I think there's a significant need to efficiently train distributed DNN jobs. And it turns out that by just distributing, sometimes the network becomes a bottleneck. And so distributing doesn't really, we get diminishing returns basically, if you're not really careful. And so one of the very first observations that we've had was that the impact of congestion control when there are multiple DNN training jobs sharing a network is actually largely ignored. This is just a cartoon that shows that suppose I had like 3 jobs and they end up sharing a link here. And we all just rely on the good old TCP or RDMA congestion control algorithm, and we hope that the congestion control algorithm is going to converge to the right fair share and everything is going to be flowers and roses, basically. So let me define the problem of congestion. What we do today is that there are schedulers that place workers based on topological approximation. We don't like congestion, so we want to avoid it. But the technique that we often use is that look at a job in isolation and try to place the workers really kind of close to each other. And so cross job, we try to avoid cross job, but I'm going to just show you an evidence that cross job is kind of inevitable in some cases. This is a very simple example. Think about like maybe a cluster with 12 servers, and here's this distribution. Here's the switch here, and then 4 servers are under the switch, and then there's also a hierarchical switch on top. And suppose that I have a training job that requires 6 servers. These servers could be DGX boxes, they could be GPU or TPU or whatnot. So another job comes in and it also requires 6 servers. And because the way that I've built my cluster, then this server needs to talk to this server for exchanging the model parameters that they've updated very frequently. And then this server needs to speak to this other server. So just placing workers topologically close to each other doesn't always avoid the problem of congestion. So I'm going to talk about what would be the impact of congestion control algorithms when the jobs are sharing a network link. This is kind of like a thought experiment. But then kind of a spoiler is that fair congestion control protocols are not necessarily beneficial for ML workloads. This is surprising, and I'll show you the surprising result and why this is actually a true statement. So let's just start small though. Let's think about a very simple case where I have 2 servers connected to 2 switches and with a bottleneck link with a link of 50 gigabits per second. Suppose that these servers are running RDMA, the default RDMA. And let's think about what would be the link utilization of this link over time. So what happens is that there's the off period when this is a compute phase. These 2 servers are both computing on the batch of data. And then there's a communication phase when they are communicating the model parameters with each other. Together, these 2 consist of what we call a training iteration. This is just the very first training iteration, but then training just continues after another batch of data and another batch of data. So this traffic pattern kind of repeats itself. And we observe that this DNN training often has a periodic on-off pattern of network demand. And you'll see why this matters when I'm talking about training and fairness together. Okay, so far so good. I got a training job and the traffic pattern is periodic on-off. I'm just going to augment my example a little bit. Now I'm going to introduce a second job to this setting. And now you can see that this link is being shared across these two jobs. Okay, so I'm not going to do anything fancy yet. I'm just going to use the default RDMA protocol that uses DCQCN as its congestion control algorithm. And it's going to share this bottleneck link 50-50. So okay, the jobs start with their compute phase. This is when they're not sending anything. And then here's their communication phase. And like I said, it's 50-50, it's fair sharing. And so here's what's happening at the very first iteration. Okay, nothing surprising yet. Now I'm going to play around with my parameters. Now I'm going to make the DCQCN algorithm slightly unfair. I'm going to make job 1 to take 60% of the bandwidth, and job 2 to take 40%, okay? And sure, by introducing a little bit of unfairness, now the green line, which is the more aggressive job, is taking a bigger piece of the pie, okay? Now I ask this question from almost everybody. The question is as follows. What do you expect the iteration time of job 1, in this case, to be compared to job 2? Almost everyone says, well, this job is getting a higher piece of the pie, higher share of the bandwidth, so it should finish fast, right? Turns out that it's actually not the case. This is super interesting. When I look at the iteration time, CDF of the iteration times of 1,000 iterations, this was just the very first iteration. If I just let this go, job 1 and job 2, they finish together. But not only that, job 1 and job 2 in the unfair case are even better than the fair case. So by introducing a little bit of unfairness in the congestion control algorithm of RDMA, I just manually flipped some parameter. I'm able to accelerate the training time of not only the aggressive job, but also the job that was actually not aggressive. It's getting even less bandwidth compared to the fair share. When my students showed me this result, I told them, totally wrong, this can't happen, probably a mistake in the way that you are tuning the parameters. Let's just do it again. But then let me show you why I was wrong. So let's think about this series of iterations. Okay? So I showed you the very first iteration in the fair case. Okay, for simplicity, I'm just imagining that they all start at the same job, and both jobs are starting at the same time, and I'm just smoothing the plots a little bit. The conclusion is the same. It's just easier to see things. When things are fair, the jobs just end up sharing the bottleneck link fairly over and over, okay, across time. But here's the interesting things. When things are unfair, job 1, okay, we said that job 1 is more aggressive, so they both start at the same time. Job 1 finishes a little bit earlier, okay? And job 2 has to, because it has smaller chunk of the bandwidth when they're sharing. It has to finish late. So here's when the magic starts to happen. Now the green job starts its next iteration a little bit earlier. And the blue job is starting its iteration a little bit later. Now imagine what would happen iteration after iteration. Green, because it was aggressive at the first iteration, keeps kind of starting earlier and earlier and earlier. And so after a couple of iterations, they're like perfectly interleaving with each other. And so what I end up doing is that I am actually utilizing my bottleneck link 100% of the time, 100% all the time, as opposed to here where I had idle time, sitting idle. And so this is sort of an artifact of this on-off pattern. And the unfairness in the congestion control was just a way of achieving this perfect inner link, kind of like pieces of puzzle that they got clicked into each other. Okay, so after my student convinced me that the results are correct, then the kind of a natural question that I asked was, well, great, let's just make everything unfair in the world, and then everything is going to be great. Turns out that that's not easy. That's not always true. So in this slide, what I'm showing is that we picked a bunch of combinations of different DNN models. And we are defining compatible jobs as a group of jobs for which, if I enable the RDMA congestion control to be unfair, to accelerate both of the jobs, like the example that I showed in the previous slide. Turns out that this is sometimes not true. So suppose that there are two VGG11 models. These are image recognition models. They're competing for the same link, and I make the top one unfair, and the bottom one, of course, I make the top one more aggressive. And okay, the top one is now accelerated, but the bottom job is now suffering. But if I change the model into a recommendation model, both of the jobs are accelerated. And this combination is not always like if this is a recommendation model or if they're the same model. We tried many different combinations of model, and it's not that easy or intuitive to say which job combinations are going to end up being compatible and which job combinations are not compatible. In other words, whether unfairness helps them or doesn't help. So what this means is that network operators now somehow have to come up with a way of finding out whether jobs are compatible or not. And so doing this means that we have to like play around with these iteration times and then try to slide them and see if they fit into each other. And the example I showed you was kind of really well designed to show you the effect, but then it becomes very ugly very quickly, because different jobs can have different iteration times, or the communication duration can be different. And so it's really hard to actually think about which job combinations are going to be compatible with each other. And so we came up with a new idea by representing a job using a geometric abstraction. So remember the single job that I showed you with the on-off pattern, okay? So the iteration time, suppose in this case, is 55 milliseconds. What we do is we wrap time around itself. We wrap time around a circle, and then we draw the communication pattern around this circle. Now, because it's repeating itself, you can almost guess what happens, right? All of these communication pieces end up occupying the same ribbon, the same arc of the circle, right? And so we simplify this a little bit. This has a little bit of, complications. Let's just simplify. Let me just color this arc and call this the communication phase, the phase that there is like some network activity going on. And now suppose, back to the example that I showed you. Now suppose that I have two deep learning recommendation models, two DLRM models. I color their corresponding arcs, and then I put them on top of each other on these circles, okay? Now, I think you can almost guess what I'm going to do. I'm going to rotate the circles, and I'm going to see if I can find a rotation angle where the communication phases, the colored pieces, are not overlapping with each other. This is kind of like this interleaving of the jobs. So here I can find a set of rotation angles when the jobs can be interleaved. Now, let me take two other models that I told you they're incompatible. And I'm going to do the same thing. I'm going to put the circles on top of each other, and I'm going to try to find a rotation angle where the colored pieces are not overlapping at all. And no matter what I do, there's no place where these two circles can be overlaid on top of each other without the colored pieces, without any, see here, the colored pieces are colliding with each other. Here also the colored pieces are colliding with each other. So we call these jobs incompatible, and they cannot be interleaved. So, okay, what do we do? What if the jobs have different iteration times? So what I showed you was kind of a simple case. Now, suppose that there's a job with a small iteration time, say 40 milliseconds. There's another job with a larger iteration time, say 60 milliseconds. putting these on top of each other is not going to work. They don't fit with each other. So what we do is that we use the least common multiplier of the iteration times, and then we create a unified circle. So suppose that the unified circle here between this 40 and 60 is 120. And so we create a circle with the length of 120, and then we place this blue job on this circle. And because the 40 to 120 is a factor of 3, the communication will occur 3 times around this unified circle. And similarly for this, the unified circle is of the length 120, and because this is 60, so the communication pattern is occurring twice. Now you can almost imagine what I'm going to place these geometric circles on top of each other, and you see here I have an overlap. If I don't do anything, these 2 colors are now overlapping here, which creates congestion. So simply, I'm just going to rotate the circles such that they don't overlap. And we can achieve perfect interleaving for these 2 jobs by just rotating one of the jobs by 30 degrees. So everything I said is kind of like figure and geometric abstraction and whatnot, but it's very easy to translate all of these into an optimization formulation, where I don't expect really you folks to read this, but just the intuition is that given a set of jobs and their compute and communication pattern in isolation, what we will do is that we calculate the compatibility score and rotation angle for each job using just this simple optimization formulation that minimizes the overlapping region. Okay. And so using this sort of notion, what we kind of propose to the community is that machine learning schedulers should be augmented to not only take job placement on servers, but also take compatibility when we're placing jobs on links. So when we are placing jobs, instead of thinking of job placement on workers, we should think about job placement also on links and put compatible jobs on links. But that's not the only thing. Once we put compatible jobs on the same link, we have to come up with some ways to artificially create this effect of unfairness for compatible jobs. There are kind of multiple ways that we can create this. And this is kind of a result of a hotness paper that we're about to present actually on next Tuesday, in fact, in Austin. And so in the paper, we argue that there are multiple ways you could have an unfair transfer protocol. You could have maybe a packet priority mechanism on the switch, or we could maybe translate these rotation angles to time and then perfectly schedule flows accordingly. Okay, so this was kind of the first half of the talk. I want to just pose a question and then I will pause to see if there are any follow-up questions regarding the first half of the talk. Everything I said kind of brings a design question in mind, that can we just avoid cross-job congestion altogether, maybe with a clean slate ML-centric cluster, okay, without maybe a cluster that doesn't have congestion at all. But before I go to the second part, I want to pause a little bit and see if there are any burning questions about the first part.
If there are questions, feel free to raise your hand or write. There is one. Timo, go ahead.
Yes, so how you presented it so far, the only dimension was the rotation angle, but can we also, by altering the batch size, for example, change the circumference of the circle so that we could make jobs more compatible with each other, or jobs that are not compatible by default, we can make them compatible?
Yeah, I love this question. Thank you for asking. I think the answer is yes. It's so interesting. Machine learning has so many hyperparameters that we may be able to make them compatible. I'm thinking about it. I don't have an answer, but my hunch is yes, your idea will work. Okay, any other questions?
I'm not seeing any, so we can continue and have another set of questions at the end.
Perfect. Okay, so now let me talk about the second part of the talk of optimizing network topology. So by now, we all kind of remember this on-off traffic pattern. This is sort of the traffic pattern in time. Now let's think about the traffic pattern sort of in space in terms of amount of traffic that a source server is sending to a destination server. And what's kind of interesting here is that you see there's this, some servers are sending traffic to some other servers, but the rest of the cluster seems kind of quiet. So we saw this, and then we started taking some measurements from distributed training job production, distributed training jobs at Meta. And what we see here is that the traffic pattern is predictable. The on-off pattern is predictable for one single job. But then when I look at multiple jobs, different jobs, like may they be vision or image processing or whatnot, different jobs have different traffic patterns. Turns out that this is actually super useful for optical networks. It's almost like a match made in heaven. Why? Because think about it. We need high bandwidth networks for DNN training because the networks are being bottlenecked, and there's a lot of articles that show this. We don't want to build a full bisection bandwidth network because it's expensive and it's unnecessary. Like I showed you in the traffic pattern, half of the graph, half of the heat map was empty. And so it's very expensive to build a very full bisection bandwidth network and then leave it empty. But then traffic pattern repeats for the entire duration of the job, like I've been showing you, whereas different jobs have different traffic patterns. This is fantastic. This is really good for optical networks because then we can have a clean slate data center that basically partitions the network for each ML job. So this is a project that we introduced called TopoOpt, which is a shardable data center interconnect. Imagine that at the bottom of an interconnect or a data center, you got N servers, okay? And suppose that each server has D interfaces. These are, think of them as NIC, the network interface cards. For instance, the servers that Meta has, they have already 8 NICs at each server. And so each server, each NIC will be connected to an optical switch equivalent to the number of NICs. And so these optical switches, by connecting the ports inside the optical switch, kind of think of them as mirrors. Like imagine that each of these dots are a mirror. And so I can change the mirror for these two, the light to be reflected between these 2 points, or the light to be reflected between these 2 points, so that these 2 servers are now connected here, or these 2 servers are connected across each other, and so on and so on. So if I have such a cluster that can adjust based on the traffic, the question is that, what should I do? How should I change these mirrors? But before getting there, I want to show you the impact of parallelization strategy on traffic pattern. So I showed you this deep learning neural network at the beginning of the talk. Let me just go a little bit deeper into what this is. This is a recommendation model that companies like Facebook, Meta, or Google, they really use this for personalized ads, personalized information to their users. It has these large embedding tables that has basically information about users and say, you know, female, 30s, buying shoes in Boston, and like connecting all of this information to inside these embedding tables. But it also, the model also has some other parts called multi-layer perceptrons. So the kind of a common technique that is used today is to distribute the model, put the model across every worker, but then distribute the data set between all of these users, between all of these accelerators. So suppose that I have 16 accelerators. These could be 16 GPUs, they could be 16 servers. So the common approach is to put the entire model on every single server and then distribute the data between them, okay? And this models, these accelerators, they need to synchronize their model parameters through a step called O-reduce. a very common technique for all-reduced is a technique called ring all-reduce. And so what happens is that because these embedding tables are really large, the amount of traffic that ring all-reduce creates is several gigabytes. In this case, 44 gigabytes. This is massive. This is a lot of traffic. But that's not really where the industry stops. The industry actually takes a step further and decides to chop off some parts of the model. So basically, these embedding tables that I told you they're large, what people usually do is a method called hybrid data and model parallels, where they put these embedding tables. Suppose I have 4 embedding tables. One sits here, and one sits here, one sits on node 8, and another one sits on node 13. So now this way, I've reduced the amount of traffic that is going across the nodes by distributing my embedding tables. So in this case, I'm able to reduce the total amount of traffic to 4 gigabytes only. But look what I did. I created these extra green hyperparameter updates, activation updates, I should say. And so these diagonal blue line corresponds to the part of the model that is repeated on every single node. And these vertical and horizontal green lines are corresponding to updating the activations and gradients because of these embedding tables that are sitting not just on every single server now, but on only 4 of the servers. Turns out that these let's just call them model parallel and data parallel flows. Okay, and so model parallel flows are these green flows, and data parallel flows are these blue flows, and they have different traffic patterns. So the blue traffic, the blue dots, correspond to this, what I was telling you, ring or reduced traffic. And these green ones are corresponding to every node sending their parameter updates to E3 and vice versa. Okay, now given this traffic pattern, the question is, what would be a good topology for a DNN training job? Well, okay, if you ask me, I would just say, create a shard that exactly matches the traffic matrix. This seems like a very reasonable approach. Given a traffic matrix, create a shard of the topology that matches exactly this traffic matrix. If I have this traffic matrix that is just a diagonal traffic matrix, okay, it's great. Let me just create a ring topology with just the amount of traffic going, just a really high bandwidth between these 2 nodes. But this is not easy. What happens is that because the traffic pattern is actually non-uniform, and I only have some number of interfaces, not everybody can be connected to everybody. So I have some limited resources. If I have infinite resources on my servers, and if I have infinite network capacity, sure, I can do that. But because I have limited resources, I'm not going to be able to match this traffic pattern exactly. It will be very challenging to build a data center that matches the traffic pattern, because it really depends on the degree of and the number of these horizontal and vertical lines. So, okay, what would be my option? Maybe I could just build a topology tailored for these large flows. It seems like a reasonable decision. So assume that I have 16 accelerators or 16 servers, and each of these have 3 possible NICs. They have degree 3. What would be a reasonable decision here? Well, if I just want to respect this really dark blue lines, I would just create 3 rings basically inside of each other. Right? This is great. This is really good for these blue, large blue traffic, but it's not that great for the green flows, because each green flow potentially could go to 8 hops to get to its destination. So let's flip it though. Let me now build a topology tailored for these short flows. So, expander graphs, they're very famous. They have pretty good diameters. And so I could just create a random graph or an expander graph that happens to have a link between, say, node 0 and node 8 to help with the latency of these short flows. But because this expander graph is random, what I end up doing is that I kind of happen to just give one link to between node 0 and node 1. And this is not enough to satisfy this large traffic. And so the intuition here is kind of right, but the way that we build expanders is not exactly tailored for this sort of traffic pattern. So the key idea we have is something that we call mutating. We mutate the traffic matrix. Let me tell you the intuition first. In networking, we are used to take a traffic matrix and then do something with it. Maybe find load balancing approach or build a topology for it. In legacy data centers, the traffic matrix is often given to us and we don't think about changing it. The key idea here, the beautiful idea here is that for machine learning, actually some of the traffic is changeable. We don't have to totally respect this. And let me show you why. So I told you about this ring traffic pattern, right? Okay, I'm going to draw another perfectly valid ring, which creates a slightly different traffic pattern. This is a perfectly valid ring. The operation is to connect and perform an all reduce across these nodes. So here 0 goes to 5, 5 goes to 10, 10 goes to 15, 15 goes to 4, so on and so forth. You can almost see this is a perfectly valid ring. I can also create another perfectly valid ring. 0 goes to 13, 13 goes to 10, and creates a different traffic pattern. So we basically, instead of marrying to the traffic matrix that's given to us, we can think about creating different kinds of rings and then putting all of these together. And so remember, I had only 3 network interface cards, right? Imagine that by putting all of these together, now I'm able to spread my traffic across all of these rings such that I can satisfy the demand. I can have a lot of high bandwidth between the nodes that are communicating with each other a lot, because I no longer have that super dark blue line anymore. So I can afford to have one link between 0 and 1, but also for these green model parallel traffic, I can have a low diameter, because this is kind of like an expander graph, but it's a well-defined expander graph to some extent. And so the key idea is to leverage the mutability of the traffic matrix to have high bandwidth for data parallel and low hop count for model parallel flows. The immediate next question is, well, there's a lot of rings. Okay, this was 0 to 1, 1 to 2, 2 to 3, etc. I showed you 0 to 5, 5 to 10, 10 to 15. There's also another perfectly valid ring by just flipping 2 of these arrows. There's another perfectly valid ring by going like this, kind of zigzagging, and so on and so forth. So in fact, there are n factorial different options. And which of these options are good, which of these options are not good, it kind of really, it's hard to find. So what we did was that we've divided all of these possible rings into sort of 2 categories: regular permutations and irregular permutations. Regular permutations are the ones where every server is connecting to another one with a fixed distance. And then irregular ones are the ones that don't have a fixed distance. And so instead of dealing with all of the n factorial options, we are considering permutations that are connecting hosts with some distance delta. In this case, delta is 1 because every node is followed by its next node. And in this case, delta is 5 because 0 is connecting to 5, 5 is connected to 10. And you see there's like a 5-unit hop count between them. And so by connecting these and by considering only these, we just reduce the search space of all these potential rings from n factorial to n. And it turns out that this is actually very easy to implement in Nickel. Nickel is NVIDIA's library for communication collectives. And so we ended up implementing these sort of regular permutation rings in Nickel. And routing is also straightforward because there's just like a nice rule to follow. So here I'm just showing you 3 different rings. This one is delta equals 1, 5, and 13. And by just combining all of these together, we end up dividing the traffic and load balancing the traffic across these perfectly valid rings. So let me tell you about two slides about the evaluations. We built a test bed of all of this. This was pretty massive effort using optical patch panels, basically, that reconfigure the network topology. And I think this is the only known test bed that allows topology and parallelization strategy co-optimization and changing of the network topology for machine learning workloads. And so on the right-hand side, I'm just showing you an example of one of us training a VGG model across a topo-opt cluster, which is the cluster that I'm showing on the left-hand side, with a regular fat tree. And what we want is to train the model up to a target accuracy. What I'm showing here is that our approach hits the target accuracy almost a factor of 2 faster than the traditional approach. I'll just show you one slide about experiments and simulations. And so this is kind of a typical way in networking, where we are simulating a cluster with 432 nodes. And the degree of each of these servers is 8, and they are connected with 100 gigabits per second links. So we're running multiple jobs, a mix of jobs that are arriving with some Poisson process and whatnot. And by increasing the load, what I'm doing is that I'm creating more jobs arriving into the system. And remember that our approach ends up sharding the cluster, but a fat tree approach will not shard the cluster. Here, the red line is showing an ideal switch. This is the perfect thing in the world. If I had an ideal switch that connects all of these 432 nodes together with these 100 gigabits per second links, then the 99th percentile iteration time would be here. And it's not increasing because this ideal switch can support up to the 100% traffic. Oftentimes we can't build this, or almost never, we can't build this unless we build up approximated with a full bisection bandwidth fat tree. But oftentimes full bisection bandwidth fat trees are expensive. So we approximate them with some oversubscribed fat tree, which is basically, think of it as a fat tree or a switch which doesn't have a full bandwidth between every server. And so naturally, by increasing the load, the training iteration time increases. What's really interesting is that for us, we're actually approximating almost exactly the perfect switch. And the fat tree, this is a cost equivalent fat tree, which is sitting up there. And this fat tree is training, or our approach is training 3 times faster than this cost equivalent fat tree. The rationale is kind of easy actually to think about it. The normal fat tree is suffering a lot from congestion. It's suffering a lot from not having the perfect topology. And our scheduling, our approach is enjoying a very dedicated topology to itself. And this topology is actually co-optimized with the traffic, with the parallelization strategy. So it's almost like everything is in perfect conditions for us. Okay, so I have about 4 or 5 slides for the next part, but I could take a pause here, or I could just zoom through and then leave the last 10 minutes for questions. What's the preferred approach?
How about you zoom through and then we can batch all the questions at the end.
Sounds great. Sounds great. I agree with that. Okay. So I want to talk very quickly about a very recent work in my group that I just want to gauge the interest in this topic. So I've been talking about optimizing network so far with congestion control and with topology, but let's just go a little bit more fundamental and think about, if the goal is accelerating machine learning, then the main operation is matrix multiplication. Matrix multiplication is not just the only operation in machine learning, but it's the major operation. It's also, matrix multiplication appears in a lot of other domains like Fourier transforms, linear equations, computer graphics, and whatnot. And so what's really interesting is that there are a lot of accelerators that are trying to make computation fast, but they're all hitting a bottleneck at the clock frequency in the digital domain. And the key idea that I want to present here is to use photonics, not for communication here, but for computation here. And the beauty of photonics is that the computation is super fast. It can run at 100 gigahertz. So the way to just put the idea in your head is that an ALU, a digital ALU, has two operands and a result. A photonic ALU is kind of like that, except that the computation is done not using transistors, but a device called a modulator. Modulator is actually a very commodity device. In all communication devices, in the entire internet and all data centers, we use modulators to modulate light. So by modulating an incoming carrier signal, but in light, we could create another signal whose amplitude is equivalent to the value of the operand. And then the beauty of this is that by modulating this signal now twice, now this is the carrier onto this modulator. By modulating it twice, I'm able to calculate the multiplication result of these two signals. And then we can just collect the results through a photodetector. These modulators, unlike transistors have clocks. Modulators don't have clocks, it's just material. And so these modulators can actually perform this operation in super fast, hundreds of gigahertz. And this is not my invention. This has been demonstrated in multiple Nature papers and whatnot. The problem with all the today's demonstration is that the photonic piece is fast, but the end-to-end computation is slow because there's maybe a Python script or some other sort of a script, C even, that is running the data into the photonic and then reading the result back. Not only they're expensive devices, but because we are putting this control into the data plane, the end-to-end compute speed is very, very small. It's just doesn't even make sense to use them. And so the idea that we have is to replace all of the shenanigans with a system on chip that can match the performance of a photonic chip. And what we've been working on is to how do we separate, kind of like if folks are familiar with OpenFlow and match action tables, the idea is similar. By separating the control plane from data plane, we want to match the really high speed of photonic devices. I won't bore you with the details, but I'll just flash the prototype that we've had so far. And these devices, this is one of the modulators, this is another modulator. These you can buy today from a website. And the same thing as the photodetector. And the FPGAs also we can buy today. So we're putting these together and we're trying to multiply numbers and then perform training and inference. I'll just show you the accuracy of a multiplication result. So what we're doing here is that we are selecting random numbers and then multiplying them together. One in using a digital ALU and once using a photonic ALU, basically this setup, okay? And what I'm plotting them is I'm plotting them against each other. And so ideally, I want everything to be on this line. And you see the multiplication result is not that bad. Given that machine learning is kind of forgiving to errors, our simulations show that this is actually quite acceptable for a lot of DNN models. The last slide I want to show is that one of the results that we've had so far, this is not a complete project by any means, but one of the results that we have so far is super exciting. And we are able to put a very small 4-layer model, these are the number of neurons, on an FPGA. And then by putting in handwritten data, we end up reading this result by all the multiplication is performed in the optical domain. And by just looking at these numbers, we're able to outperform a GPU 100 times. Part of this is because of our optimized data path. Part of it is because our photonic is running faster. I'm just gonna skip this and then let me just bring you to the last slide. I hope that I tried to convince you that there's a lot of opportunities to optimize networks to accelerate ML workloads. And what I said was about congestion control and topology and whatnot, but I don't think this is really the end of the game here. And so with that, I'm very happy. Thank you very much. And I want to take questions. I want to allow some time to take questions. Thank you.
Okay. Thank you so much, Manya. Before we move to questions, just a Quick advertisement, our next BCAST seminar will be on the 1st of December. We have Dejan Milošić from HP Labs, who will be speaking.